Okay, good morning, everyone. So you all survived the party last night. Good to see you all here. Last day, last session of the event. So welcome you all to today's session on SRv6, network troubleshooting, where you're going to learn about implementation best practices also. Before I begin, I was going through the registration list, and I saw most of you are from service provider background. So let me ask you this thing. When you were starting your SRv6 journey, at any point did you feel that MPLS wasn't that bad at all? If so, you're not alone. So SRv6 is going to bring your, is going to simplify your network a lot. It's going to increase your scalability in many-fold. At the same time, it might seem difficult at the beginning, which is not true, and we'll see how it is. There are a lot of moving parts, some new concepts. By the end of the session, you'll see how it is easy to navigate through the SRv6 maze. I like this statement from Mr. Charles Kettering, who says, a problem well stated it's already half solved. And which means you don't need a solution for a problem. You just need to understand the problem. Once you understand the problem, you'll definitely solve it. You'll find the solution. So that's what we're going to do today. So we're going to understand the problems well. We'll start off with some basic concepts about SRv6, and we'll learn about SRv6 microSID, control plane and data plane troubleshooting, and we'll use those concepts to solve some real-world failure scenarios. I've got 3 use cases for you, and in the end, also you'll learn how to design your network better to avoid such problem scenarios to arise at the first place. Little bit about me. My name is Ashish Panda. I'm a senior technical leader with Cisco. Last 15 years, almost, most of my career I'm in service provider TAC organization. So problem is my bread and butter. Not many of you love problems, but that's what I do. I solve problems every day. I'm a dual CCIE. I've written this book on Wireshark forensic. I have a few patents in the service provider space, and from the personal side, I love playing cricket. I love going to the mountains. Above all, keeping everything aside, what I value the most is the learning that I get from interacting with you, the customers, the service providers, over the years. The learning, I feel privileged to have that practical learning from the real-world issues, and that's what I want to show you today. We're going to learn from practical problems. Okay. I just wanted to remind you about the questioning and answers. So you can always put your questions in the WebEx room. Time permitting, I can take a few questions every segue, and there will be a dedicated Q&A session towards the end. I'll reserve some time for that. Okay. Before we get started, just few basics. What are all the discussion that we'll have today will be based on SRv6 microSID, even though we'll touch SRv6 full-length SIDs. The world is moving towards SRv6 microSID. That's what our focus is going to be. And all the discussion configurations are based on iOS XR, although same concepts apply to different platforms or different vendor altogether. And always you can keep in touch, keep yourself keep your learning going on the segmentrouting.net. There's a link to the latest SRv6 book also in the same link. I put it here. So let's get started off with some basics of segment routing. So what is segment routing and how it evolved? Segment routing is routing based on segments or instructions. So we call instructions as segment IDs or SIDs. You'll hear this terminology quite often, SID. So when we started with the MPLS world, so every instruction was a label. So you want your packet to go through your firewall, load balancer, then the internet gateway out, or whatever way you want it. Those instructions you put in terms of labels, a stack of labels, and you create a packet at the edge and send the packet to your network. Right? That simple SRMPLS. When IPv6 backbone came, same concept we took. Instead of labels, we had IPv6 stack of instructions as IPv6. We call full-length SIDs. And each SID in IPv6 SRv6 world is 128-bit, 16-byte. Right? So you can see the challenge, right? And I'm sure I see some familiar faces from Lenos session last on SRv6 basics. The challenge with SRv6 full-length SIDs is it can increase your label stack overall, your header length, because every SID is 128-bit, right? And we realized that we don't need all 128 bits to define an instruction, right? All we want is to tell the router that, yeah, go from here to here, right? That can be simply done in 16 bits. And that's what we did with SRv6 microSID. We compressed that instruction of 128-bit to 16-bit as a microSID. And we'll learn with a practical analogy how it is better, basically. Say, I want to send a package from India to Australia, to Melbourne, basically. But I want the package to go through a particular path. Say, I want the package to first go through Perth, then Adelaide, then Melbourne. So the first way, I create a nested envelopes, 3 different envelopes. First envelope, I write the Australia full code and then the city. Every envelope, I write the same, Australia and the city, Australia and city, right? And every hop it goes, and then the envelope comes out, the top one, and it goes to the bottom, like that. Or the simpler approach could be, I write the Australia country code, because anyway, Australia is only one, right? Once. So I write Australia only once, and then I write only the city codes, in a sequence. Same thing, what we are doing with SRv6 and SRv6 microSID. SRv6 microSID makes things simpler, leaner, and agile. Let's see with an example how we are doing it. So we have something called locators in SRv6 microSID world. Locators is nothing but it locates a node, right? So every node, if you have 1,000 nodes in your network, every node will have a locator or identifier. So we support 3216 format, which means the first 32 of the bit of the locator is the network portion, Australia, right? And the next 16 bits identifies the node, which is, say, Perth, Melbourne, Adelaide, like that. So if you see this example, so first FCCC 0001 is the network portion. That remains same on every device. But 0215 will change from device to device, right? So in this case, say device 1 wants to send the packet to device 215. So it will just refer its locator and create a packet, put that destination address, which corresponds to your locator 215, and send the packet out, right? Suppose within that device, you might have multiple services, right? Services means you have L3 VPN service, L2 VPN service, multiple such instances. So how to identify those service instances? So the service instances are also identified with a SID or the microSID. The microSID for the services is locally significant, whereas the node SID 215 is globally significant, which means 215 cannot exist anywhere else in the network. But your local service identifier for your service is local, and it starts with E00. And like if you're there in the last session, your adjacency SIDs are locally significant, right? Something similar, right? So that's where when the packet has to, when the router 1 has to send a packet to VRF, corresponding VRF, it will just append the local service identifier and send the packet out. And when you're quoting your local microSID E001, it cannot exist alone. It has to always be associated with your node identifier. So always you'll have the node identifier, locator, plus your local service identifier, right? So let's see, with another practical example, how the packet looks like. The actual packet with microSID will look like this. Okay, you will have a source address, source IPv6 address, and destination IPv6 address. Your destination IPv6 address will contain your microSIDs. Okay, in this case, I want my packet to go through router 1, 2, 3, 4. That particular path I want the packet to go through. So what we do, first 32 bits will be the network portion of the destination address, FC01, DB8. And then the sequence or the path that the packet wants to go to, we put the microSIDs corresponding to those locations in a sequence, right? In this case, we put 1, 2, 3, 4. And we have the service identifier, which is E002, right? Which is for that particular VRF. Okay. The key point which I want to highlight in this is the destination address that you see in SRv6 packet will keep changing at every hop. Okay, and that address doesn't exist anywhere, right? No device in your network will have this address. We have created an address, or basically we have encoded this address, right? So in this case, some terminologies. The first encoder, the complete 128-bit we call as a carrier. Out of that, the first 32 anyway, we know it's a network portion we call SRv6 SID block. Okay, that will remain same. The 16 bits that follows the SID block is called active microSID. All your forwarding works on the active microSID. So whenever the router has to send the packet out, it will always look up the 16-bit, which is following your network portion, right? And other microSIDs will follow after the active microSID. Okay. Okay. So let's see how the actual forwarding will look like. Say router 2 in this case got the packet. So what it do is it will look at the active microSID, right? All forwarding works on the active microSID. So the packet in this case, you see the active microSID in this case was number 2. And the router locator also, in this case, has also configured with the microSID of number 2. The locator, if you see, FC01, DB8, 2, : 48, which means its own microSID is also number 2. What the router does in this case is, if the active microSID is equal to its locator identifier, it'll do a left shift. It'll remove that microSID and do a left shift. Okay, and whatever is resultant, it'll do a forwarding based on that. So when you do a left shift, what will remain? 2 goes. We have 3, 4, right? So then the R2 will see, yes, where do I send the packet towards 3? Okay, the next 3 is the next microSID, right? It'll say interface 001, and it'll send the packet out towards that interface, right? Okay. With SRv6, what happens is, whenever you allocate a microSID, when the router allocates a microSID, it allocates. Also, it defines clearly what is that microSID for. Like the purpose is also clearly identified. We haven't seen this in SRMPLS ever. which is a great thing, right? So we only used to get a label, and we didn't know what is that label for. But in SRv6 microSID, you know, when you get a microSID, you know what that microSID is for, right? In this case, you can see from this command output, very important command, you will use it quite often. So segment routing SRv6 SID, it will list to you all the microSIDs the router has allocated, right? In this case, you know, it has, you can see what is the microSID, which is mentioned in the blue, and the corresponding behavior for that microSID, right? I'll just you know, name a few. UN means node identifier. We saw that what is a node identifier. UA means adjacency microSID, right? It is same as what you saw, what you're familiar with your SR MPLS world, adjacency SID. UDT4 means L3 VPN. UB6 means you've got a SR policy. We'll see more in detail about that, right? So all these behaviors, this slide lists out all such supported behaviors and also documented the corresponding RFC for that. Okay, let's see how to bring up your SRv6 network. Pretty simple and straightforward. So what do? Under segment routing, we enable SRv6, and then we create locators. We name a locator, locator main. You can have multiple such locators, up to 8 is supported. So why do you need different locators? So you need locators for different algorithms, different purposes. So if you want a forwarding behavior for shortest path, you might have a behavior which is corresponding to your low delay forwarding kind of behavior. For every kind of behavior, you create a locator. Simple, we created one locator in this case. And we define the locator prefix, so which is your node identifier. So BB00101. And then what we do is we map that locator to your routing protocol. So your routing protocol can be IGP, can be BGP, depending on your purpose or service type. Okay, simple. We support 3216 format. First 32 has to be network portion. It has to be remaining same across your network, and next 16 should be your network, your node identifier. Okay, you configured your network. You thought it's very simple. You know, all your devices should be forwarding your traffic, but sometimes, yes, UDC issues, right? It might be because SRv6 is not supported on your device. You need additional configuration. Why do you need that? Because what is happening with the forwarding is SRv6 changes the whole concept. Your packet destination in IPv4 world or MPLS world never changed, right? Destination IP v4 never changed. But with SRv6, it changes at every hop, right? You do a left shift, then forward, left shift, and forward. That needs a platform support. Your ASIC, forwarding ASIC has to support it. So in the DNX platforms or the Broadcom ASICs on these platforms, 5500 and say 540, 560, you need this particular command to enable that forwarding behavior. And a chassis reload is required. Similarly, for NCS 5500 with J2 cards, you support only on the native mode, which means there's a mix of, if there's a mix-up of J plus and J2, we don't support that. Only native mode supports SRv6 forwarding, and after you configure this command, you'll need to reload the device. Okay, with this, everything should work. But your question is probably, yes, how do I identify? Is it the same issue or not? As a network engineer, what we do, first command that we check is show log, right? So when you do a show log pipe for SRv6, it will clearly show that it failed, and what is the reason for that. Okay, pretty good to find out. Okay, let's quickly dive into troubleshooting SRv6 control plane. Control plane means signaling your IGP-related issues or your BGP-related issues. And it can manifest in multiple ways. Your SID, what you're advertising probably is not, when you're receiving it's different, or maybe you're not receiving it at all. Your policy is down. So all such issues, let's quickly dive one by one. Okay. So for the IGP case, like we support only ISIs, first command to check is show SRv6, so segment SRv6 seats. What all seats the router has allocated. So once you configure that basic configuration, once you do, the router will automatically allocate the microsets, right? So what all microsets it has allocated, this command will show you, and corresponding behavior. And SRv6 is nothing but normal IPv6 routing. So every microset it has allocated, it will show up as normal normal IPv6 routes. So if you do show route IPv6 and local SRv6 corresponding routes for SRv6, it will list out all the local routes, all the sits as local routes. So locally we know we have checked, but my remote PE, PE2 is advertising some microsets. How do I know sitting on PE1 if I'm receiving those or not? Quick thing to check is routing table again. So route IPv6 ISIs, it will show as again routes. The remote microsets will show up as routes in your routing table. Okay. If you do deep dive, so route IPv6 for detail, it will show as locators will show up as locator keyword. And say suppose you're not getting it. So how do we get it from PE1 to PE2? We use ISIs, right? So ISIs uses LSPs. You check detail of that particular LSP, which PE2, your remote was advertising. And you filter for your UN, UA. It will show you the corresponding node sets, node microsets, and then adjacency sets. OK. So ISIs, we have extended ISIs with the additional TLVs, which supports all this transporting of all this information. So TLV 27, and under the TLV 27, we have got multiple sub-TLVs, 5, 25, 43, 44, to transport the UN and UA microsets. And you can check quickly in the LSP. So ISI's database and corresponding LSP, it will show the details of those microsets. Okay, and this is output from, if you want to do a packet capture in a network and capture that LSP, it will look like this. Okay, now we always say that SRv6 is backward compatible, which means even if your device, some of the devices are not capable of SRv6 forwarding, you can still have the packets forwarded by those. How is it possible? Right? That's not possible with MPLS, right? So it's possible with SRv6. How? Because that locators that you have configured, along with the new TLVs, the older TLVs also we advertise. The older TLV is TLV 236 or 237, which is multi-topology TLV. So using that, so basically we are advertising the same thing at two places. So you can verify that with ISI's database command also with the and see the same metric what you have for the TLV type, the other TLV, which is 37. And it's again a capture which shows that. Okay, so within the domain it's okay, right? ISIs will populate and transport all those sets. What happens across the domain, right? With MPLS or SRMPLS, what we used to do? We used to use BGP-LU to stitch that, right? So you have got domain 10 on my left and domain 20 on my right. So we use we leak those loopback addresses and stitch using BGP-LU. So if you have got 1,000 routers in domain 1, you will have 1,000 prefixes coming in from your source domain, right? That causes your scalability issue. How to avoid that? With SRv6, we don't need that. So if you don't need it, then how do you do it? So what we do is we do summarize. I told SRv6 forwarding is like simple SRv6, normal IPv6 routing or forwarding. What we do in normal IPv6 routing, we summarize at the domain boundary. That's what we do. At every domain boundary, we only send /40 prefixes. So our locator is /48, right? 48, if you summarize to /40, how many you can summarize? 256, right? So instead of sending 256 prefixes, we are sending only one summary. Okay. So with that, you see so route IPv6, you can filter all those summaries using /40, and then you see only one summary going out. Okay, with that, I'll dive a little bit into services. Before that, what questions do you have? I can take one. If not, you can always put in the WebEx room. Okay, L3 VPN and L2 VPN services are very common. So I'll start with L3 VPN. You all are familiar with L3 VPN. You use configure VRF, and then when you configure in SRv6, something changes. What changes? Your service or VRF will get a service identifier. In this case, on your right, if you see, you create particular VRF has got an identifier E002, and the locator is 104, and service identifier is a microsite for L3 VPN is E002. Okay, and that we advertise using VPN v4 as usual, and that receives your source P, receives that, and then using that, when a packet comes in, that complete SID is programmed into the packet destination as IPv6 destination that goes out to your network, and when it reaches your destination, that gets stripped off, and the original packet comes out. Simple L3 VPN. Okay. Now, how to configure? Configuration again is simple. You have already created the locator in the beginning, and you have attached to ISIS. Now, you attach that locator to your VRF configuration under the BGP. Simple, straightforward. And once you do that, it will allocate that microsite, which is E006 in this case. And whenever we allocate a microsite, we also told that we clearly define what is that microsite for, the purpose. So in this case, the behavior or the purpose is UDT4. UDT4 means when you get the packet, you strip off that packet, and T means table, 4 means 4. So if it's like IPv4 prefix that is coming in, you remove that packet and do a table lookup in IPv4 table, right? That's what we do. You can also configure, in this case, the allocation mode is per VRF. It can be per CE also, but we don't support in some of these platforms at the moment, but the support will come. So once you, let's see how to validate that and how to check what kind of troubleshooting scenarios can arrive. So once you configure that, the first thing to check is what are the local sets, right? So the similar command, familiar command, so BGP, particular VRF and local set, if you do, it will show what are the local sets allocated. On the remote side, you go and see, validate that it is matching with what is being advertised. So in this case, you see, so you have to use the received keyword. If you see, it is matching, right? Ingress and egress, it has to match. If there's an issue, you'll not see that matching. How do we transport? ISIS, we know we had some TLVs. BGP, how we are transporting that prefix, these microsets. We have extended with some TLVs. The details are in RFC 9252. I put the link. So I will just focus on things that you should be knowing. So what you see here is your label value or the service identifier is going in the label value field, right? E002, 0. Normally, in the MPLS world, it used to be 20-bit labels, right? Now, with SRv6 microsite, it's 16 bits. How do we take that 16 bits from that 20-bit? That is defined using the transpose length, right? Your locator information is coming in the SID field. SID FCBB BB00104, right? We don't get the complete information. So how do we get the complete information? At the bottom, you see transpose length 16, which means take out 16 bits from the label field and then transpose it with the SID information. So when you do that, what will happen? 104 and E002. So this particular complete address is used by your ingress to put the packet, put into the packet destination address. Correct? Sometimes you might see this label information incorrect. We'll see that scenario. So let's see the imposition scenario. Imposition means when your PE gets the packet from your CE, it has to put that SRv6 header. Basically, the IPv6 in the IPv6 destination, it has to put that information that we just saw, right? How to verify if it's putting the correct information or not? So first is show route, as usual. If you do a show route lookup for your IPv4 under that VRF, it will show what are the SID list that it is injecting, right? Same thing, you can, because it's an IPv6, complete SID, you can do a route lookup for that particular SID. It will show you the destinations the packet should go to, right? You receive from your access, the packet should go to your core, right? So you do show route for that particular address that you're injecting. It will show what is the path it will take. Same thing you can verify with the forwarding lookup. So SRv for that particular IPv4 prefix under the VRF, if you do, it will show what are the complete SID list and the path the packet will take, right? And disposition means when the packet reaches the destination, what the destination router will do. And it'll just do a lookup, right? What kind of lookup? The packet will be coming with the IPv6 destination address as a complete SID that was injected in the imposition side, right? So it does a lookup for the show route IPv6 for that local SID that it has allocated. So from that, it will give you the table ID or the VRF identifier. And then if you do again, if you do a show SRv for that, the forwarding lookup for that, it will give you it says that do a lookup in the table, right? And then you do which table? The table details also is seen as 100, which is VRF 100. So then you go to show SRv VRF 100, do a lookup again for that IPv4, and it will give you the destination that the packet should go out, which means the packet comes from the core, it has to go to access side with CE, right? 3 simple steps which will clearly show you how the packet should travel at the disposition side. Let's quickly see a couple of real problem scenarios. First scenario, your CE receives the prefix from, PE receives the prefix from CE using BGP, eBGP, address family, but it is not advertising to your, destination PE or route reflector. Normally, you'll see if there's a filtering or anything. In this case, we don't have any filtering. So first thing to check is simple steps. First, we check what is allocated. In this case, we see the top one, the allocation was blank. So per VRF allocation, it was blank. Normally, whatever you've configured, what we have configured is allocation mode as per CE, right? But it is not showing to us. And we see the no service seats allocated as no on the top side. That is really bad because if BGP doesn't know what the BGP actually has to transport as SRv6 prefix, right? And until unless you allocate the SIDs, it will not be able to transport. Because we saw that allocation is not showing correctly, we configured it to pers VRF mode, and then that helped it. The SIDs were populated, and BGP was able to transport. The key learning here is it was unsupported configuration in your platform, right? So how to identify that? It's clearly see the allocation mode. If it's blank, then you should go ahead and correct it. Okay, next scenario. Your microSID, which is received from your source PE, is different on your destination PE. And if you see in this case, my VRF, we have allocated E002. On the receive side, we are getting 5D E1, right? So simple step what we do, PE1 we checked, so BGP VRF for that particular prefix. We're getting E002 as the microSID. But when you're receiving, we are receiving in the BGP, we are receiving, what do we receive? In the label field, right? In the received label, we are getting 5DE1, which is incorrect. How is it possible? We always see this SRMP less, right? So SRMP less in the BGP, the label keeps changing. Because in your middle PEs, you configure next hop self. When you do next hop self, it changes the label also, along with the destination next hop. So same thing happens in SRv6 also. If you do it, it will change. But ideally in SRv6, we don't need it, because what we do is we do summarize and send the prefixes, right? We don't need to change the next hop. So that's the problem in this case. So when you correct it, it all got sorted out, right? OK, let me quickly jump to some EVPN BGP troubleshooting. So EVPN, for the L2 services, we use two common service types, which is E-line service and E-LAN service, right? VPWS is E-line service. In the E-line service, VPWS has got one source and one destination. PE1 sends the packet to PE4, only one destination. So how it does, whatever L2 packet it receives, it just injects an SRv6 SID, sends the packet out, which gets stripped off at the destination, and the packet goes out. Configuration pretty straightforward. I'll not go much into detail of that. But once you configure it, right, what to verify is your local SIDs and remote SIDs should be matching, right? In this case, for your particular service, EVPN, VPN ID 200, whatever the bottom one lists out what are the received SIDs and what is it allocating itself. I just want to focus on a few things which might be interesting. So in this case, how are we transporting that particular prefix microsets within that BGP? So EVPN, we use address families, right? Address family, it can be within EVPN address family, the route types can be 1, 2, 3, 4, 5. So using route type 1 for this VPWS service, in this case, the behavior that you see is 65 for that particular prefix. If you paid attention in the L3 VPN case, it was 63, which means L3 service. 65 means UDX2 behavior, which means L2 service behavior, right? And the label value, the particular microSID for that L2 service is also again, coming in the received label field. But the actual label field is 24-bit in this case. And the transpose length will show you how many bits to take out from that label field. In this case, we see transpose length is 16. So we take out 16 bits and attach to the SID value, which is B00104, right? Okay. So let's a little bit about troubleshooting BPWS. First thing you should check is what is received. Is it matching with the sending side, right? So you see, you do the received SIDs command. You get microSID is 101 E003, and you verify same thing on the SRv6 SID command on the remote one with the allocation command. So a segment routing SRv6 SID. Both are matching. So the next thing to do is imposition kind of troubleshooting. Imposition means when the packet is received on the from the CE, it has to inject that microSID, right? We know what to inject because we know the received information. So what we do in EVPN scenarios is, even though it's L2 service, we treat it as like L3 service. In L3 service, we have a VRF, right? Same thing we do here also. So but we don't have actual VRF. We have got an internal VRF. So to do the lookup for the internal VRF, we have to find out the internal identifier. In this case, the familiar commands for L2 VPN X connect, you find for your service, you find out what is the internal identifier corresponding to your L2 VPN service. In this case, 10.0.0.1, you take this and do a route lookup in the internal VRF. So route VRF internal IID, the name will always remain same, ** IID. And then you do it, it will show what is the microSID it is injecting in this case. The full SID length sequences FCBB 104 E005. Okay. Same thing you can check from the sourcef internal VRF command. And if there is a mismatch, there is an issue. Disposition case is something similar again. Disposition, the packet will come as an IPv6 packet, so it has to do an IPv6 route lookup. So how to identify what prefix to do an IP lookup? You see what is being allocated locally. So L2 VPN XConnect group, familiar command if you do, the local microSID is FCBB BB0 E003. In this case, if you do a lookup for that, it will show the corresponding interface the packet should go out. Right? You do the same for the same command, and you see the interfaces and the details the packet needs to go out. Correct? Okay. E-line is something similar. E-line is almost similar. But what I want to show is in this E-line service, what is different is it's kind of a broadcast or multicast service also possible with E-LAN, right? So in SRMPLS world, how we used to do? SRMPLS world, we used to have a unicast packet. We had a different label for unicast packet, different label from multicast packets. Same thing we are doing here. So we have got a different, when you configure E-LAN service, you'll have different microSIDs allocated for your unicast and multicast packets. So the behavior would be corresponding to unicast UDT2. For multicast, it would be UDT2M. How to identify corresponding microSIDs? So segment routing, SRv6 SID all, same command. You find out what are the corresponding microSIDs, right? And in the BGP table, again, the command that is already given. So if you pen RD, you do RD lookup for the received SIDs, it will show you what are received. Now we saw that the forwarding is like a L3 forwarding, and we need an internal identifier to be found out. How do I find out that internal identifier? The first command will show you. So L2 route EBPN MAC. Okay, corresponding to the MAC, you find out the internal identifier, and then do the same lookup how we used to do in the E-line service. I will not go much into detail. But I just want to show you the route types in this case. For your unicast microSID, you use route type 2, right? And the same kind of transposition will happen. For multicast UTM kind of SID, we use route type 3. Okay? And the third route type we use is route type 1 again for the split horizon label. So E-line service, we used to have split horizon. So why do we need split horizon label? If you remember SRMPLS, your packet that you're sending can again loop back to you, right? In layer 2 domains, LAN, you always have loops. To avoid such loops, you need a split horizon label. So that's what we do with SRv6 microSID again. We use route type 1 to transport that split horizon label. And it's a little bit different. What we do is we attach that split horizon label with the original type 2 label, right? Type 2 microSID. Okay, I'll quickly jump to FRR, the protection. What questions do you have before that? Okay. Sorry? Okay, I'll go quickly into that. So you configure your services. IGP you have configured is L3 VPN, L2 VPN is configured. But services can go down, right? When your links go down, your node goes down. So how to protect that? You learned about TILFA, same thing we're doing here. So TILFA will protect in all such failure scenarios. So in this case, say XR2 wants a packet to send to XR7, one hop away. If the primary path goes down, the packet should go to backup path. So what we do in this scenario TILFA, same concept, we calculate a P node and Q node, right? So which means if you send the packet to Q node, it will never loop back to source. So the key thing in TILFA is you have to find out the P node and Q node. Your ISIs will do that for you. So in this case, your ISIs, if you do so ISIs IPv6 fast readout for that particular SID, in this case FCBB 007, 7 corresponds to XR7, right? If you do, it'll show you the P node and Q node, right? And then how we do it is in SR-MPLS world, we used to send the packet to the node SID, and then we used to attach the adjacency SID to the next hop towards the Q node. Same thing we're doing here, right? So the SID for P node in this case is FCBB BB008, and then the adjacency SIDs towards the Q node is E003. So when you attach it, what you get, the same details you can find out from the sourcef command. Sourcef IPv6, if you do a lookup for that, it will show your protect path is using the insertion of this particular complete SID, which is FCBB00E8 E003, right? Let's see how it works when the actual packet goes out. We can quickly see what we did was we initiated 1,000 packets and initiated that failure scenario, and when during that failure scenario, it'll protect for some time. So when you take a packet capture, you can quickly see your the IPv6 destination is equal to what you see in your CEF table. If you don't see the same thing, if there is a mismatch, then your packet might be dropping. So you might have such scenarios arising in your network at some point. So quick thing to note here is, so normally when we started with SRv6 microSID, we said that we don't have SRh, right? SRh is a concept of your full-length SIDs. But in TILFA scenarios, you'll see an SRh coming in because some of your devices may not support. And whatever your original ping, you're pinging to BB71, that is put into a SRh label. So and you see only the destination, a different destination, which is corresponding to your Q node. So that is, again, protected. That whole packet is encapsulated and stripped off. We have the original information available so that we can recalculate it when we receive it. Okay, little bit about traffic engineering. So you know how to protect your network with using TILFA with, again, SRv6 microSID, but how to route the packet through a path that you want, right? We use traffic engineering or SR policies. Same thing, we'll do SRv6 microSID traffic engineering policies. Configuration is pretty simple and straightforward. You create locators, which you already know. And then you define the SID format for your traffic engineering. So in this case, 3216, same. And then in this case, I have created an explicit path using the path identifiers. I'm using the node SIDs 104, 105, 108, and then use that locator to map to your policy. And your policy, I'm identifying with color 100 and endpoint to whichever destination I want the packet to. And to go to the destination, use this explicit path. So we have attached it. Straightforward. So once you configure, it should come up, right? Sometimes life doesn't go the way you want. So if the policy is down, what to look for? The important thing that you should be looking for is the error, right? And you should see what is the last error, and the operational status, and the your path code, error code. And also when the policy is down, you'll not see anything in the forwarding output. So segment routing, traffic general forwarding, policy, nothing you should be showing. All such, you can have various type of errors. It may be inactive policy, it can be invalid path, it can be different like invalid SID list. So this slide talks about all of those and all the explanations. In a working policy, it should show you like a admin up, operational up, and it should show you the complete SID list that you have defined. And it should show you binding SID. So the binding SID, is something the router refers to when it wants to send the packet through that policy, right? In this case, binding SID is E007. There are ways that some services want to use this policy, some doesn't want it. So only when you want your packet to go through the policy, then you quote that E007 number. And this command will show you the statistics and the complete forwarding details about that policy, if it's programmed correctly or not. Okay, almost through the data plane, like we're almost there at the data plane troubleshooting. Any questions related to control plane before that?
Just notice that we need to declare microsets again under traffic engineering. I thought we were already declaring it at the hardware level. Do we need to again declare it?
For the explicit path? Okay, the question is, do we need to configure the microsets for the binding SID?
Yeah, there was a command where you mentioned that under the traffic engineering, segment routing traffic engineering, you have configured that.
Let me go to that. Yeah, this one? Yeah, the SID format only we're defining. SID format only we're defining because you may, it's common for, like, you can have full length SIDs also. So when we come to, we explicitly define here, okay, under the micro.
The global one doesn't apply directly over here if you don't define it.
Yeah, explicitly we define it here. Good question though. Okay, let me quickly jump into the data plane troubleshooting. So data plane troubleshooting scenarios will arise when your control plane looks good, your BGP is good, all your prefixes, values that you're seeing good, but still you have issue, right? So there, the packet can be dropped at any location, and how to identify it can be pretty complex at some point. But I'll tell you three simple steps which will help you identify where the packet is getting dropped, why it is getting dropped. Okay. First thing, SRv6 troubleshooting is simple like IPv6 troubleshooting. It's simple IPv6 forwarding. Nothing changes here. So normal IPv6 forwarding, what you used to do? We used to do pings and traces, right? So that's what we do. We do a ping to your SRv6 microSID. In this case, it is successful on your right, you can see, and the trace also, it will show you the complete path the packet is taking through, right? The second thing that you need to do is, if you see a packet is failing, right? You have to identify from the trace, it will show you where it is dropping. That's an indication that yes, something is wrong either on that location or something before or after that, right? To validate that, you should be using packet counters, statistics, or doing a packet capture, right? Packet capture is pretty complex in MPLS. SRv6 makes it simple. SR-MPLS or MPLS, if the packet is on the core, it's very difficult to capture because you have got volumes of traffic, like gigs of traffic, and you cannot do a packet capture simply only for that packet easily. With SRv6 microSID, you don't have labels. What you have is an IPv6 address, simple. IPv6, how do you normally capture? You use either can use an access list simply to define very specifically to that packet, check the access list counters, or use that specific access list to capture that packet, and all the capture mechanisms support access lists easily, right? That makes your troubleshooting very simple. The third step is once you find out, yes, where the packet is dropping, yes, I have validated using all the statistics and counters. I'll use the SRv programming, like routing lookup, forwarding lookup, and then that will give you some more details. Along with that, you'll have logs and traces also you'll do, right? So what is new and what is additional, what is beneficial to you in addition to that is your carrier-based pings and trace. So what does that mean is when you can define the path that you want your packet to go through only, simply at the pings and traces also, right? Normally that is not possible, right? When you do a ping IPv6, you only define one destination. With carrier-based trace, you can define hops that your packet can go through, right? In a failed path, if you see your packet is your SR policy is through a particular path, you can quickly do a trace using those hops in the trace command itself, right? For a failing trace, it will show you, yes, it is failing at this location. For a working case, yes, it will show you, whether it's successful or not successful. Okay, let's quickly dive into some real-world use case. Let's utilize these concepts. Yes, there's a question.
I have a question in regards of the trace hop. So is it available for VPNs as well?
Is it available for VPNs as well? Okay. Okay. So for VPNs also, you know what is the corresponding microsets, right? So you do a trace route for the corresponding microset. It may be L2 VPN or L2 VPN, doesn't matter. Once you know what is the microset for my L3 VPN, I'll do a trace route for that, simple.
Outside the VPN?
Outside the VPN, yeah.
That's not the way we used to do MPLS, right?
That continues, right? So if you're doing like IPv4, so you do route for that particular this thing. So route for your IPv4. So trace for you do a trace for that particular IPv4. That anyway will continue. But right now, it not so when you're doing from outside, it will not show the internal hops. So we'll have a feature which will support. Which will show the internal hops when you're doing from outside the L3 VPN, from the CE side, right? But as an operator, it's easy to troubleshoot when you know what is the corresponding microset. You do like from the global table, and it'll show you the path.
The same thing on the trace route with the explicit hops. So you can't force it to return the traffic on the same path so you have asymmetric return path with that. Is that an issue?
So if you want, like always you trace to the destination, right? So if you want to a return path, then you go to the destination. From the destination, you do trace of the return path. That also you can do. Okay. Thank you. Okay. I hope there's no more questions in this room. We can take it in the end, of course. We've got a L3 VPN scenario, same use case. We've got a big domain, big network. We've got two domains, ISIS 10 on my left, ISIS 20 on my right. And then we're doing summarizing in between. Our problem is from PE1 to PE7, when we're taking the red path, the packet is getting dropped somewhere, and we to take the packet through that path, we are using a SR policy. When we set that policy, the packet takes the IGP path, and everything works fine. My ping works fine, my trace works fine, everything is good. We have to find out what is going wrong. Classic scenario, right? Every service provider we do. So how do we start? We start off with some basics, control plane troubleshooting. Control plane troubleshooting, simple step, verify what you're sending is same as what you're receiving or not. So we went to PE7, we verified what we are allocating in this case for that particular VRF. That prefix, when you do a lookup, it shows the SID that is being allocated, in this case 207 E005. E005 is the microSID allocated for that particular VRF. Okay. Now we came to this ingress PE, and we verified with the same command, so bgpvrf for that particular prefix, and we see E005 is received in the label field, which is expected, along with the SID total locator information in the SID field. Correct? We transpose that and we get the complete information. Also, what we see in this case is we have got the prefix is pointing to a binding SID, which is the micro SID for that is E007, and the color is 610. So, which means you on the head PE1 head end, so we have got some policy configured, SR policy configured. So we verified what are the policy details, right? And also we can see that the policy is up. The path that we want, which is like 3, 5, 7, that is also correct. And the binding SID E007 is also matching with the prefix. So everything looks fine as of now on the head end, PE1, right? So what is going wrong? Let's move a little bit towards the core. So the next step, control plane was okay. We'll do data plane troubleshooting. In data plane troubleshooting, what we said, 3 simple steps, right? First step, trace. When we traced, it showed that it went to 3, but it is not going to 5, right? In the SRh, the next hop was saying was next hop was 5, but it didn't go to 5. It dropped. So clearly there is something, some issue on the 5. Now we did a ping. So policy-based ping also is possible. Along with like normal ping, you can ping a policy, segment routing SRv6 policy, and the policy name, it is dropping. So we've got an indication that it is probably dropping at 5, but we need to validate. Second step of data plane troubleshooting. How to validate? So we generated packets. We check the stats, right? First step is incoming packets on my incoming interface. Is it matching with my outgoing interface? On PE1, it is matching, and PE3, it is matching. But when we did same thing on P5, it says that received packet is 1,000 plus, but sent packet is less, which clearly indicates P5 is dropping. Okay. At this point, you should be doing packet captures, or you can use access list or statistics to find out, pinpoint that yes, it is being dropped here. Now, the third step of data plane troubleshooting is the route lookup and self lookup. So we went to PE1, we verified without policy, with a SR policy, it points to the destination locator PE7 and the corresponding micro SID E005, which is correct. Okay, but when we enable the policy, it is pointing to the binding SID. Okay, which is 101 E007, which means it is going through the policy when we activate the policy, which is correct. Okay, so PE1 is fine. So let's go to P5, which we think that it is dropping, right? So we did the same thing, so self lookup, and we see that there is a drop adjacency. Okay, drop adjacency means your forwarding plane is considering the packet to be dropped. Okay, so this is the reason why it's being dropped. But just pay attention to the particular, pay attention to the lookup prefix, right? I'm doing lookup for 5207, right? But originally the packet was coming with 35 PE7, right? I didn't mention 3 here. Any reason why I'm doing lookup for 5207 only? No. We do shift and forward, right? So when P3 sent the packet out, it does a left shift. It removed the micro SID for itself, which is 3. And then that's why you're doing a lookup for 5, right? So when you're doing lookup in your core, you should be doing the corresponding correct prefix lookup. Okay? So it is clear, because it's not programmed correctly. But why it's not programmed? You verified the logs. You can also check the traces. It clearly shows that there's a programming failure happened for that particular prefix. Okay? Sometimes it is not supported by the platform itself. Sometimes you've not configured the original commands. If you remember, for the platform support, we didn't configure. All such cases are possible for this particular logs. Your data plane issues can be manifesting in many ways, right? Your symptoms and the causes can be different. But whatever may be the issue, you just apply this three simple troubleshooting approach, three-step approach. You'll reach a conclusion why the packet is getting dropped. Okay, some additional commands or steps I have for you. What you can have is the platform-specific commands. After this, all SRv6 commands, right? We enter the hardware troubleshooting, which is normally like for the tech domain or the engineering domain. So I'll not go much in detail for you today. But there are some important commands that might help you again. So the scaling is sometimes you might end up scaling, having scaling issues, which means the number of locators that you have configured. I mean, the prefixes are very high, or either your platform doesn't support all of those. The TCAMs, all of those you can find out from the segment routing SRv6 manager. Very important command. I've just snipped it, but the important output that I've shown, which can show the number of locators, supported, number of locators available, all of those. The command on your right is show NPU resources all, which might also help you if your hardware resources are depleting. Okay. All of these you can avoid when you have best practices deployed in your network. When you design your network, you can avoid all such scenarios. Let's quickly dive into what are those best practices. But before that, let me tell you, I didn't cover all of those SRv6 concepts, all the features that is supported. Of course, we didn't have much time. So what are the commands required for troubleshooting all of those important ones I have mentioned here, and what to look for in those commands I have mentioned in blue, right? So that will definitely help you. You can keep it as reference. Let's quickly dive into best practices. Okay. The first question I get is, or when you are designing, you will have is, what should be the locator range, right? We support FC00, which is like a ULA address, locally significant. Locally significant within your domain, it is significant. It's not routable address. Routable addresses, the global unicast addresses are supported, but we don't recommend it. The second space, which is 5F00, is also reserved for SRv6 kind of applications. It is also recommended and supported. But normally you'll see 95% of deployments you'll see with the first approach, which is FC00. The 5F00 is valid, and it is we are catching up. So once you know what is the locator range, you'll have questions how to structure it, right? Structuring your locator helps in many ways. There are no defined right and wrong, but this is what the best practice is. You have the structure that we recommend is FC is constant anyway. 32, and we said we support 3216, which means 32 is your network portion, 32 bits, and the 16-bit your node portion. So in this case, the SID block, 32-bit portion, so we have FCBB, BB, and then the last 2 hex fields we reserve for your algorithm address. Say you want to have a locator for your strict path, or you can have for low delay path. So up to how many locators you want, you can have it up to late. So that algorithm type we reserve for the last 2 hex numbers. So in this case, if you want a low-cost path, low-cost slice, it can be 00, whatever it can. If you number your low delay slice as number 1, that number should come here, right? So we sorted out for the first 32-bit portion. What about the next, the node portion, which is the next 16-bit? 16-bit can have up to 65,000 addresses, right? But you don't want your domain to go high, 65,000. So what we recommend is you should split your network into smaller domains, each having maybe up to 256 addresses. So we split it into first 2 hex addresses. 02 in this case is, we say, like, reserve it for domain identifier, next 2 for your node identifier. So in this case 15, right? So we call the domain identifier as set identifier also. Say suppose you have got 600 routers in your network, in your domain. How many sets would you need? Sets of 256, right? So divide with 256, you need 3 sets in this case, okay? And then within that set, you have your next portion, 15 in this case, to define your locator. With a practical example, let's see. So you've got 600 nodes, 3 sets. Say we say allocate set 2, 3, and 4. So your node, say 7 in this case. Just an example. Node 7 will be part of the first set, which is set 2, and the node identifier is 7, right? So the complete node set is 0207. Similarly, for your 518, node number 518. Node number 518 is for set number 3, and the set number 3 is for the set ID for that set number 3 is 04. So 04 and 06. 06 means 512, after 512, the 6th node after that, which is 512 plus 6, 518. That's how you number your nodes structurally. So if you follow a structure, how it helps is it helps you summarize. This is the power of summarization that helps your network scale up. So what you do is, because you have structured every 256 nodes, you can summarize into /40 summary addresses instead of sending all 256 specifics. So what we do, in this case, 600 nodes, but we are sending only 3 summaries, which is /40, right? Instead of sending each /48 600 prefixes, we're just sending only 3 summary addresses. Think of your network of 1 lakh devices. How immensely it is going to help you scale up. Right? Same thing we do at every region. The right side region also, we send only summaries. The middle region also, we send summaries to each side. We don't have any specifics anywhere. Summarization is a double-edged sword. It helps you, but it comes with its own challenges. Okay. The summarization hides the actual information. So when it hides, your packet can take a suboptimal path. Right? In this case, just for an example. So your ABR, 2 domains, your right side domain sending summary, /40 summary. Your locator 2011 and 2012 are being summarized with 2000 address, right? BB00 2000 /40. Right? When you advertise a summary in ISS, you also advertise a metric along with that. So we're advertising metric of 100 for both the summaries. So when PE1 receives that prefix, the bottom path it will receive as 101, and the top path it will receive as 102. So it'll find out. It'll say that yes, I want to reach PE11. To reach PE11, PE1 will take the bottom path again, right? Because that is the shortest path for it. PE1 has ABR2 closest to itself compared to ABR1, right? So the packet takes a suboptimal path in this case. When the path goes down between these two, still the packet will come to PE12 and it will get dropped on PE12. It will not go to PE11. Okay? In this case, we have got an open ring. So what we recommend is we should have a closed ring architecture. How it helps when you have a closed ring. So closed ring means between ABR, you have something joining, right? There's a cross link between ABRs. So when you have a cross link, how it helps? Now, even though the packet comes to ABR2, which is closest to PE1, it will take the cross link to reach PE11. It will not take the suboptimal path. And even if the link between PE11 and 12 goes down, there is a path available through the cross link to reach PE11. Okay. Okay. Sometimes you may not have feasibility of having a cross link. Your ABR is in one in Adelaide, somewhere the other ABR is maybe say Melbourne or somewhere else. There's no direct connectivity, back-to-back connectivity. So how do you do in that case? So we have something called a partition detection feature. In this case, what the ABRs do is ABR1 tracks ABR2 and vice versa. And when the link goes down, ABR1 sees that yes, we have got a partition which is the domain is partitioned. When the domain is partitioned, it will suppress the summaries. Okay, ABR1 will stop the summary advertise. ABR2 also will stop the summary. And they start advertising specifics. So in this case, if you have got say 500 routers, you might end up having 500 specifics going into your core, but that's temporary, as long as your domain is partitioned. So when the domain when the link comes up again, those specifics will be withdrawn. Only the summary will be advertised, right? So one more important feature that we have is unreachable prefix announcement. So when you have summary, and you have got two paths to reach CE1, it's P11 and P12. From P1 side, left to right, the packet has to go. Summary is being advertised, but when P11 goes down, but there is still a path available to through P12. In this case, how does P1 know? Because the summary is not changing, right? And the packet can come through your network and get dropped somewhere, and it get black holed. To avoid such scenarios, we have got the unreachable prefix announcement. So what it does is, in case of failure, it also advertises a specific along with your summary. So when you have specific advertise, we have 2011 UPA kind of prefix, not a normal advertisement. And when PE1 gets that UPA advertisement along with the summary, it triggers the PIC, BGP PIC recalculation. So using which, the next, at PE1, your next hop will point to PE12, right? And your packet will successfully go to CE1. The third, or the important one, the question that I get is, what should be my loopback architecture? So, I mean, sometimes you might have a greenfield network. You're just starting off SRv6 configurations, or sometimes you might have also a brownfield scenario. You already have SR or SRMPLS or MPLS, and you're moving to SRv6. What should be your approach of loopback configuration? So you already have a loopback address which to pair with your route reflector for VPN v4, VPN v6, or SRv6 purpose. And the second challenge or the question that comes to your mind is, also you have to encapsulate your IPv6 packets when you send to your network. So use some address to source that packet. So what should be the source loopback interfaces in both the scenarios, for the BGP peering and for the SRv6 encapsulation? Our recommendation is, if you have a greenfield network, you have both as same. So you configure your loopbacks in the locator range. So FC, what is range we have seen? FC00 range or a 5F range. From that range, you allocate your loopback, say 0, and then both are for the same purpose. You use both. But if you have a brownfield scenario, there are other ways possible. But the first approach, what it helps is it helps you reduce the number of advertisements. You only advertise only one prefix for the locator. If you use the other two scenarios, you'll end up advertising the BGP prefix and also the locator prefix. All of the separate recommendations, small recommendations, what we have is for the SRv6, when you're bringing up, you should always have separate route reflector for SRv6. Okay, even if you already had route reflector which you configured for your VPN v4 and other services, existing services, you should use a different route reflector for SRv6. The important concept is MTU. Your SRv6 packets can grow a little bit high depending if you have an SRH coming in. SRH might come in TILFA kind of scenarios. So you should keep that into your account when you're designing your network, defining your MTU and your path. So what you should be accounting for is IPv6 header for 40 byte, SRH header for 8 bytes, and additional SIDs that will come up as IPv6 addresses of 16 bytes. Okay, for resiliency, we should be using Anycast if you want also fast convergence. So if I want to summarize the key SRv6 advantages, right? So simplicity to its core. Less protocols. We don't need your RSVP or any other protocol. Only your ISIs can do it. You don't need BGP LU to stitch your domains together. Your summarization helps you scale up your network way higher than compared to an existing network. And we have got service compatibility, what you have in your existing network. Compact header, your MPLS header was like 4 byte, right? Complete. Now with your SRv6 microSID, it's completely half. We've got 16-bit at 2 byte, if I can tell you. And when you compare to SRv6 full length, it is manifold, right? So one SRv6 in one IPv6 address, we can stuff 6 microSIDs or 6 instructions. And it is highly programmable. You can define wherever the path you want the packet to go to. The multiple services, service chaining, or service anything that you have your mind, SRv6 can support. SRv6 forwarding is like classic IPv6 forwarding. Your router in your path may not support SRv6, but it will still be able to forward your packets, right? Your troubleshooting is like classic IPv6 troubleshooting. It makes your life very easy and simple. If I want to summarize what you learned today, so simplicity to its core. SRv6 makes things simple. Also, troubleshooting-wise or network design-wise, it makes things very simple. It's kind of back to basic, if I can tell you, years back. We use simple tools to understand the control plane troubleshooting. Like what you're sending, you should be able to receive, map, check, everything is fine. Same thing with data plane troubleshooting. We learned 3 simple step approach to find out any data plane issue, how to troubleshoot, and also we had the flexibility of carrier-based pings and traces. And we also learned some design best practices that helps you reduce all those troubleshooting scenarios to rise at the first place. So if I want to connect back to how we started, a problem well stated is a problem half solved. I would say if you state a problem well, it's completely solved. Once you know what is the problem will be there no more, right? And With that, I want to remind you, to complete your evaluations. And of course, today is the last day, but you can still, for the next time, you can always book your MT sessions in advance, meet with some expert if you have queries. And always you can visit the on-demand library for more such contents. And I've got the link for the book, SRv6 book, just at the beginning. So lot many contents in the SRv6 net page also to continue your learning. And I want to thank these amazing persons who helped revise this content. So thank you so much. And I want to thank you all for your time and attention. I want to remind you that do put your questions in the room. I always value your feedback. Please complete your surveys. It helps us, not only me, it helps Cisco improve. And I always respect, it may be positive or negative. I always respect. So, and I read each and every question and feedback. So definitely, you can feel free to put everything that you want. Okay, with that, we are open for questions. What questions do you have? Yeah.
In the microsid format, the service identifies E and 3 hex digits, right? So is that limited to 4,000 services, or is there some way to have more than that if you need it?
Okay, good question. The question is, with microsid format, should the microsid start with E? No, it is for E is only for the local microsids. So there is a global block and local block. For the locally significant microsids, we start with E and goes till F, E0000 and then FFFFF within that. So that is 16-bit again. That can go up to like 65,55336. So quite a bit.